About 300,000 years ago, our ancestors faced a paradoxical situation. Advanced cognitive abilities helped ancient peoples solve everyday tasks, find food, make mates, and engage in self-defense. The more developed the brain was, the better it modeled reality, allowing people to mentally look into the future. However, increased intelligence led to an unpleasant realization that comes with the realization of mortality. By witnessing the death of their kin, humans realized their inevitable fate. About 300,000 years ago, in some ways the most unpleasant event in history took place. The first living creature on Earth reached a level of consciousness that allowed it to realize its own mortality. Humans appear to be unique in their awareness of this aspect, with little evidence to the contrary. On the one hand, this understanding can paralyze us, because what is the point of doing something, of trying to choose some life path, if all paths lead to one single place, to the cemetery? And yet, here we are, not extinct, and seemingly unaffected in our understanding of reality. How have humans managed to survive, and not even degenerate to a more comfortable level of understanding of reality? What fundamental adaptation mechanisms were they able to develop to resist the existential anxiety caused by the realization of their own mortality? How do we find the determination to continue living in the face of impending danger? In 1973, the American anthropologist Ernest Becker presented a groundbreaking perspective in his Pulitzer Prize-winning book, The Denial of Death. According to Becker, this denial is the only adaptive mechanism that conscious beings, including us, have rapidly evolved. The book argues that much of modern culture is a complex coping mechanism, often unconscious, arising from the fear and anxiety each person feels when realizing the inevitability of his or her demise. If a man recognizes that he has absolutely no control over the death that lurks beneath him at every turn, if he allows this thought to take over his consciousness, he will sink into such fear and trepidation that he will be on the verge of insanity. Ernest Becker. Consider death row inmates who face an increased risk of psychotic delirium, a manifestation of the death row phenomenon. This phenomenon emphasizes the high likelihood that people are essentially defenseless in the face of various existential threats. Whether it is a report of an impending meteorite impact in 5 years, the potential annihilation of humanity by a powerful artificial intelligence in 20 years, or the catastrophic effects of global warming in 50 years, people may be unable to take meaningful action, even if they had the opportunity to do so. Thinking about abstract threats to life is considered a maladaptive survival strategy. According to Becker, it is not the only strategy, but a predominant one. One common way of denying one's mortality is to believe in an afterlife. Billions of people hold some form of belief in an afterlife. While many argue that advances in modern science have destroyed the concept of an afterlife, this claim is only partially true. Science, to put it bluntly, cannot definitively eliminate all humanly devised variations of postmortem experience. Science itself occasionally puts forward intriguing concepts, such as the idea of quantum immortality, which derives directly from the many worlds interpretation of quantum mechanics. This interpretation assumes the existence of a multiverse and was originally proposed by the brilliant physicist Hugh Everett. Quantum immortality serves as an extreme means of demonstrating the existence of multiple parallel universes. It's a method that I don't recommend you try to replicate at home. It is essentially the same as the famous Schrödinger's cat thought experiment, but the experimenter is the cat. In the proposed scenario, a gun is pointed at the participant's head, which will or will not go off, depending on the decay of some radioactive atom. Consequently, the risk that the gun will go off and the participant will die is 1 in 2. According to Everett's interpretation, at the moment of the experiment, the universe decays into 2 parts, one in which the participant survives, and one in which he or she perishes. In a world where the participant survives, the experiment is repeated countless times. From the observer's perspective, there is no experience of the universe splitting, and the concept of nothingness remains elusive. Thus, only the perspective of the surviving observer prevails, and the experiment continues for as long as he wishes, without leading to his death. If the participant survives after 10 consecutive repetitions, he may exclaim, Hugh Everett was right, given that the probability of such a sequence of survival is 1 in 1024. If the experimenter manages to survive 100 consecutive times, it is unlikely that anyone in his universe will have any doubts. I emphasize, in his universe, because in that case, the probability of survival drops to this probability. I have no idea what that number is called. However, in a long experiment, the universe divides not just into two, but into a larger number. There will be universes in which the gun went off, but the experimenter, experiencing a seizure, dodged the bullet. In these diverse universes, there are possible scenarios where the gun misfires, and even cases where the atoms that make up the bullet synchronously disperse in different directions, splitting the projectile before it reaches its target. Developing this idea, it can be argued that, in reality, the probability of death at any given time never reaches 100%, even at the epicenter of a nuclear explosion. In the vast majority of universes, the observer will inevitably encounter death. There is always a thin layer of universes in which an improbable event occurs that allows the observer to survive. In this way, the observer gains some form of personal immortality. However, this intriguing concept has a caveat. Personal immortality does not guarantee the observer's well-being. If quantum immortality turns out to be true, it could lead to a personal hell in which a person cannot die, no matter how intense his or her suffering. Given that the probability of death at each successive point in time cannot be 100%, a person will outlive all humans. The transformation of the sun into a red giant and the demise of the Earth will eventually remain the last stronghold of consciousness, forever drifting in the vast universe. It sounds absurd, but it is a logical consequence of understanding the many worlds interpretation of quantum mechanics. So we should be happy that the existence of a multiverse is just an assumption. However, there are subtleties and gaps in this thought experiment. Physicist Sean Carroll suggests that the surviving version may not necessarily be you, but perhaps your twin. The first researcher to delve into the life of Hugh Everett, a proponent of the multiverse concept, was historian Evgeny Shekhovtsev. In a biographical sketch, Shekhovtsev writes, "Everett was a convinced atheist. He once declared that he denied the Catholic faith. Atheist or not, Everett firmly believed that his theory of multiple worlds guaranteed him immortality. His consciousness, he argued, was obliged at each branch to follow any path that did not lead to death. So on, to infinity. Perhaps this is why Everett avoided doctor's visits, ate excessively, smoked 3 packs a day, consumed large amounts of alcohol, refrained from physical activity, and died at the age of 51. In 1996, his daughter Elizabeth tragically ended her life from a sleeping pill overdose, writing in a note that she intended to join her father in another universe. Despite our attempts to construct a narrative and deny the inevitability of our own demise, there always remains the option that death will bring us what we try hard not to think of. That death is the end. The prospect of nothingness on the other side is an idea about which Parmenides, the ancient Eleatic philosopher, argued that it is impossible to reason about, because one cannot contemplate what does not exist, thereby violating his own instruction. It is about nothing that we will discuss today. Despite the fact that many people do not believe in hell, they experience a similar fear when they encounter the concept of nothing. Nothingness haunts the existent, wrote Jean-Paul Sartre in his treatise Being and Nothingness. The concept of nothingness deeply concerned the philosopher Martin Heidegger, a contemporary of Sartre who devoted many pages to exploring the concept. While human death represents a softened form of the supposed nothing, I suggest that we shift our attention to a more fundamental aspect. The nothing out of which the world emerged. One might wonder what can be said about nothingness. But, surprisingly enough, there is a considerable amount of work on this topic. Notably, 2 best-selling books, written by different authors, are devoted to this topic. One of these authors, Lawrence Krauss, is a theoretical physicist and cosmologist, and the other is Jim Holt, a science journalist and critic with habits reminiscent of Dr. House. And in terms of the relationship between these two, they're actually buddies. The video is primarily influenced by reading both books, but is based more on Jim Holt's work. This bias arises because Lawrence Krauss predominantly delves into describing the evolution of our universe since its inception. At the end of his book, Krauss openly admits that he was not actively seeking answers to questions about what might have existed before that point. Jim Holt, on the other hand, delves into deep thought, interviewing prominent physicists, philosophers, and mathematicians in search of an answer to the question of why there is something rather than nothing. By following Holt's exploration in the book, you may come to realize that nature, as we understand it, and even the concept of God, are not the only contenders for the answer to this fundamental question. By the end of the video, chances are that you will be convinced by this viewpoint. While some may dismiss the question of why there is something rather than nothing as trivial or unworthy of attention. It was of great importance to thinkers such as Gottfried Leibniz, a luminary who, contemporaneously and independently of Newton, pioneered mathematical analysis, single-handedly transformed logic, and stood as one of the greatest intellects in history. In 1714, Leibniz was the first to pose the question of why there is something rather than nothing. Arthur Schopenhauer wrote, "Those who are not interested in the question of being, in the question of world being, suffer from dementia." Stephen Hawking, in his A Brief History of Time, says, "Even if there is only one possible unified theory, it is only a set of rules and equations. What breathes life into the equation? What is the universe? They describe born out of. The traditional scientific approach, which is to create a mathematical model, cannot answer a number of questions. Why should the universe described by the model exist at all? Why does the universe bother to exist at all?" Ludwig Wittgenstein is widely known for the phrase, "What cannot be said should be silenced," with which he ends the most influential philosophical work of the 20th century, called the Tractatus Logico-Philosophicus. Even Ludwig Wittgenstein writes shortly before the end of this treatise, "The mystical is not in the way the world is revealed, but in what it is." Some would say that the question is too philosophical, but even Einstein believed that science should go hand in hand with philosophy in trying to understand nature. He wrote, "Today, very many people, and even professional scientists, seem to me someone who has seen 1,000 trees, but has never seen a forest. Knowledge of historical and philosophical foundations gives that independence from the prejudices of one's generation from which most scientists suffer. This independence, created by philosophical insight, is, in my opinion, the mark of distinction between the mere artisan or specialist and the true seeker of truth. For those who deem the question of why there is something rather than nothing as inherently unsolvable and meaningless, it's worth recalling that similarly complex inquiries, such as the composition of matter, were raised 2,500 years ago by Thales of Miletus and other pre-Socratic philosophers. Back then, the question of what constitutes matter would have appeared no more meaningful than the inquiry into the existence of being. As Oxford philosopher Timothy Williamson observed, the pre-Socratics posed one of the best questions ever asked, a question which, through agonizing attempts to answer it, led to the development of modern science. Similarly, one could have dismissed the philosophical question concerning the distinction between inanimate and animate entities. Molecular biology has provided answers to this question. Just as the seemingly impossible task of constructing a bridge from the finite to the infinite, now achieved through mathematical set theory, was once considered unattainable. Presently, scientists are striving to unify mind and matter, working towards a comprehensive field theory that links matter to mathematics. As these unifications progress, there may emerge the possibility of discerning clearer outlines of a bridge connecting the realms of nothing and something. Now, consider a thought experiment. Close your eyes, block your ears, and envision being in a total void. Strive to eliminate people, plants, earth, sky, and all elements from your mental vision. Picture the vanishing of the sun, stars, galaxies, and everything succumbing to darkness, cold, and silence through an act of will. Can you imagine nothing in this manner? When French philosopher Henri Bergson conducted this mental experiment, he discovered that ultimately there remained something, his own self. At the very instant that my consciousness goes out, another one lights up, or rather, it is already burning, for it has arisen a moment earlier to watch the disappearance of the first. Henri Bergson. Bergson found it impossible to conceive of nothing because some vestige of consciousness inevitably creeps into this darkness, like light shining under a door. Hence, he argues, nothing is impossible. If we cannot imagine nothing, does that mean that something must always exist? Not only is this plausible in the universe, but there is indeed much that exists that lies beyond the possibilities of our imagination. Consider this. Can you imagine an object completely devoid of color? Not transparent, but completely devoid of color. Think about it, and it turns out to be impossible. Take atoms, for example. They are inherently colorless. Moreover, most of us, with the exception of a few exceptionally gifted mathematicians, have trouble imagining the curved space-time dictated by Einstein's general theory of relativity, the very fabric of our existence. Immanuel Kant deems the concept of nothing as philosophically impossible, acknowledging its unimaginability. However, what if one attempts to achieve nothing in a laboratory setting? What if a specific space is chosen, and all matter and energy are extracted from it? While this seems plausible, an intriguing event arises in the process. The spontaneous emergence of something referred to by physicists as the Higgs field, contradicting common sense. Efforts to eliminate this newly appeared entity prove futile, as the Higgs field's contribution to the total energy of the space being emptied is, in fact, negative. Consequently, the Higgs field stands as a form of something containing less energy than nothing. Criticism has been directed at Lawrence Krauss's book, particularly when he asserts that nothing is, in essence, something, leading to ridicule for perceived misuse of the term. Yet, according to Lawrence Krauss, nothing is a depiction of a state where there are no particles and all mathematical fields register zero. However, this specific state is deemed impossible within the current physical model due to the constraints of Heisenberg's uncertainty principle. The principle posits that if the exact value of a field is known, its rate of change becomes entirely random, making it impossible for the field to be zero. Attempting to establish such a state of nothing is bound to result in the emergence of something. Krauss posits that nothing is inherently unstable, suggesting that an entire universe could originate from such a state. This concept was initially articulated in 1969 by a physicist named Edward Tryon in New York. During the lecture, Tryon suddenly said, "Perhaps the universe is a quantum fluctuation." Rumor has it that several Nobel laureates present burst into laughter. But today, as you can imagine, many physicists are considering the idea seriously. And if the possibility of creating an entire universe out of zero-point energy doesn't surprise you, then, for example, according to the recollections of physicist Georgy Gamow, when he told Einstein about the idea while walking around Princeton, quote, "A stunned Einstein stood up like a stump, and because we were just crossing the road, several cars had to stop to avoid running us over." Absolute nothing, on the other hand, may look ridiculous, but it is not absurd. From the point of view of logic, there can exist a world completely devoid of anything, distinguished from other conceivable worlds. It has neither space-time, nor fields, nor any stage for the unfolding of events. When we speak of this so-called world, we do not mean a material object, but rather a conceivable way of unfolding reality. Interestingly, this world is inherently supposed to be just that. Why? Because nothing is the simplest of all potential realities, and this concept was originally emphasized by Leibniz. The value of this simplicity is well known in scientific circles. The principle of Occam's razor, developed by the scientific community, states that when competing scientific theories are equally supported by experience, the scientist should choose the simpler one. The preference for simpler theories in science is not just because they are aesthetically pleasing or easier to work with. Rather, they are considered more likely. Consider the historical example of Newton, who assumed that God occasionally adjusts the trajectories of the planets to prevent collisions. Later, Laplace presented a simpler view, suggesting that introducing God into the equation as an additional entity was unnecessary. The laws of physics, he argued, effectively maintain the stability of the solar system without divine intervention. Even if you believe in God, you are still more likely to side with Laplace, because his version is more likely. However, if you believe in God, you will say that it was the Creator who made these laws. So isn't it easier to explain everything by God in general? English evolutionary biologist and ardent atheist Richard Dawkins argues that the postulate of a God who created the world in the first place is untenable because any God capable of creating the universe and then fine-tuning it precisely and providentially for the origin of our life would have to be an incredibly complex object whose existence is more difficult to explain than the original problems. Hence, the simplest of all possible theories is the theory of absolute emptiness. This theory of nothing involves no laws or entities and allows for no arbitrary assumptions. If simplicity is indeed evidence of truth, then the theory of nothing is the most probable. And then the eminent philosopher of science, Adolf Grünbaum, came on the scene and rejected the question of why there is something rather than nothing as a pseudo-problem. He called those who posed this question fools. Unlike Leibniz, Schopenhauer, Ludwig Wittgenstein, Martin Heidegger, Richard Dawkins, Stephen Hawking, and Marcel Proust, as well as numerous contemporary philosophers, scientists, theologians, and simply thoughtful people, Grünbaum found nothing surprising about the existence of the world. He firmly believed that there was nothing worthy of wonder in the matter. Grünbaum says, some scientists and philosophers gawk at the world saying, we know that simpler theories are more likely to be closer to the truth, but that's just their own psychological complexes and heuristics. It has nothing to do with the real world. Take chemistry. In ancient times, Thales of Miletus believed that all chemistry was based on a single element, water. When it comes to simplicity, Thales of Miletus's theory certainly wins the battle with Mendeleev's polychemistry. Created in the 19th century, postulating an entire periodic table of elements, However, it is Mendeleev's theory that corresponds to reality. However, we are aware that 13.7 billion years have transpired since the Big Bang. The prevalent perspective is that the universe had no existence before that point. Could this be considered as nothing? Grunbaum, however, contends that the finite nature of the universe's past holds no significance. According to him, physics does not permit us to project backward and assert that there was nothing before the singularity. This is an elementary mistake that many of my opponents make. They mentally imagine themselves at the initial singularity as observers with memories, and this gives them an overwhelming sense that there must have been earlier moments in time. However, the Big Bang model teaches us that no time existed before the beginning. Adolf Grunbaum. However, is this claim true? When it comes to the creation of the universe, Andrei Linde, a Russian physicist who moved to the United States in 1990 and has made significant contributions to explaining the origin of our universe, puts forward an intriguing viewpoint. According to his inflationary model, do you know how much matter it takes to create a new universe teeming with billions of galaxies like those observed today? Amazingly, it takes only 100,000th of a gram of matter for a new universe to emerge, essentially starting anew in its own temporal context. By comparison, a single ant's foot weighs more than that. This tiny amount is enough to create a small patch of vacuum, followed by a large explosion. Theoretically, Lind suggests that we could replicate this process in a laboratory setting, effectively assuming godlike status. Moreover, there is no certainty that our own universe did not originate in a similar way, perhaps by the actions of a civilization not too different from our own. Intuition suggests that such events should be avoided because the newly created universe would begin to expand into the parent universe, which could lead to massive destruction. However, Lindy argues that such a danger does not really exist. The new universe will expand into itself. Its space will be so coiled that, to its creator, it will appear as tiny as an elementary particle. It is possible that, eventually, it will disappear from his world altogether. In a conversation with Jim Holt, Linda suggested that the person responsible for creating such a universe would likely have only one way to communicate with the potential inhabitants. The creator could influence the embryonic state of the universe to set certain physical parameters in the created world. For example, a creator could determine the ratio between the masses of an electron and a proton. These numerical values, known as fundamental physical constants, may seem completely arbitrary to us. There is no obvious reason why they should have these particular values, such as why the gravitational force in our universe is defined by a number with the digit 6.674. By setting certain values for these constants, the creator could have put a mysterious message into the very structure of the universe. And only physicists could read it. Consider it a joke if you like. But such an assumption cannot be completely ruled out. It could explain why the world we live in is so strange and so far from perfect. Apparently, our universe was created not by God, but by a physicist, hacker, Andrei Linde. The prevailing belief now is that the new inflationary cosmology provides the most plausible explanation for the Big Bang. According to this theory, events similar to the Big Bang, which give rise to universes, occur quite frequently. It would be peculiar if the Big Bang were accompanied by a label stating, "This mechanism only works once." In essence, inflationary cosmology posits that our universe emerged from the space-time of a pre-existing universe and is just a minuscule part of a vast multi-universe, rather than being the sole physical reality. Each universe within this cosmic array has a specific starting point in time, with ours originating 13.8 billion years ago. However, the overarching self-replicating structure itself may be infinitely old. In such a scenario, there is no need for a first cause, as there is no unexplained moment of creation in the infinite timeline of the world. As noted by the eminent thinker David Hume, nothing can precede an infinite past. Every event is always explained by a previous event, and there is no end to this chain. But even if the world is eternal, is that enough to dispel any remaining sense of mystery? Jim Holt thinks not enough. Such an infinite world is like a railroad train with an infinite number of cars, each one pulling the next, and there is no locomotive. It can also be compared to a vertical chain with an infinite number of links, each link holding up the link below it. But what holds up the chain as a whole? Jim Holt. Despite the absence of a root cause, the fundamental question remains, why does the universe exist and why does it obey certain laws? After such reflections, the thoughts of many philosophers return to a concept dating back to 1078. Philosopher Anselm of Canterbury developed a logical argument to prove the existence of God, known as the ontological argument, which has intrigued mankind for a millennium. Perhaps you remember this video that we've all been throwing at each other to prove the validity of atheism. The video features Bertrand Russell, a British philosopher, logician, and mathematician who made significant contributions to mathematical logic, history, philosophy, and the theory of knowledge. So, in his autobiography, he writes, "I remember the very moment in 1894 when I was walking down Trinity Lane, and it suddenly struck me that the ontological proof was true. I had gone out of the house to buy tobacco, and on my way back suddenly tossed a tin of tobacco into the air, and catching it, exclaimed, 'Damn it, the ontological proof is correct.'" What is the essence of this ontologically proof? In a condensed form, it goes like this. God is the most perfect of all conceivable beings, but existence in imagination is less perfect than existence in reality. God, on the other hand, is by definition absolutely perfect. Therefore, God exists in reality. As you have noted, Russell later concludes that the ontological proof is not essentially true. Nevertheless, he recognizes that it is easier to be convinced of its fallacy than to pinpoint exactly where it is wrong. As an example, he cites the fact that the idea of God is not a kind of God, even though it may be considered less perfect, just as a painted apple is not a kind of apple, even though it is less nutritious. Regardless of the existence of God, the question of the depth of our comprehension of reality remains open. David Deutsch, a British physicist, pioneer of quantum computing, and staunch proponent of the many worlds interpretation, argues that no such limit exists. In 1985, Deutsch accomplished the remarkable feat of demonstrating the theoretical possibility of creating a universal quantum computer capable of performing the tasks of any conceivable computing machine. Moving from the familiar classical computer to the quantum computer, pioneered by Richard Feynman, Deutsch's universal quantum computer possesses another astonishing characteristic. In principle, it has the ability to simulate any physically conceivable environment, essentially making it the ultimate virtual reality machine. When a young Deutsch presented his proof of the existence of the universal quantum computer to Richard Feynman at Caltech, who was already grappling with cancer, and wrote down the initial formula on the blackboard, the ailing Feynman unexpectedly rose from his seat, seized the chalk, and concluded the proof himself. For Deutsch, the universal quantum computer represented the key to comprehending reality. Such a machine, capable of generating any physically possible worlds, would serve as the pinnacle of physical knowledge. It would be a singular physical entity that could be constructed and possess the capability to describe or simulate any part of the quantum multiverse with exceptional precision. In 2023, David Deutsch was awarded the top scientific prize for his pioneering contributions to quantum computing. According to Deutsch, an astrophysicist can effectively visualize a distant quasar billions of light years away. The mental representation of this quasar consists not only of an image, but also includes a structural model with appropriate causes and mathematical relationships. In front of you are two objects physically as different as it is even possible to be. Despite the vast physical differences between a quasar, a black hole with streams of matter, and a brain, essentially a chemical foam, both entities embody identical mathematical relationships. Deutsch explains that for this phenomenon to occur, the laws of physics must have a unique property that allows and even obliges them to be comprehensible. Nevertheless, he clarifies that this does not mean resolving the existential question of why there is something rather than nothing. I don't think a complete comprehension of reality is possible. It doesn't mean that I think there is a limit to our explanations. We will never hit a brick wall that says, no further explanations. On the other hand, I don't think we will find a brick wall that says, this is the final possible explanation for everything. In fact, both walls would look pretty much the same. David Deutsch. Deutsch says that none of our laws of physics can answer the question of why the multiverse exists. The laws of physics don't do that in principle. Science cannot answer the deepest questions. As soon as you question why there is something instead of nothing, you are out of the realm of science. Alan Sandage, the father of modern astronomy. Scientists are well versed in the workings of the physical universe, unraveling the causes and interactions between individual objects and forces. In his book, Lawrence Krauss delves into these explanations, shedding light on the evolution of the universe and its transitions from one state to another. Yet, when it comes to the fundamental source of reality, science remains silent. The idea of a primordial origin of the world is examined, revealing the paradoxical nature of such a concept. When Einstein finished his general theory of relativity, he saw that the equation explicitly said the universe must either expand or contract. No third is given. Einstein, much like many physicists of his era, was firmly convinced that the universe lacked a beginning. To support this belief, he introduced an additional element, the cosmological constant, into his equations, effectively positing an eternal and static universe. However, when confronted with compelling observational evidence, Einstein later acknowledged the cosmological constant as his most significant error in life. Observations indicated that we inhabit the remnants of an enigmatic phenomenon. Although the concept of the Big Bang is now familiar when examined abstractly, it seems absurd and contradicts our intuitive understanding. The idea that all the material in the universe originated from a single point challenges our intuition. Unsurprisingly, British astronomer Fred Hoyle, credited with coining the term Big Bang, dismissed this theory as pseudoscientific. In a BBC program, he said, "The reason scientists like the Big Bang is because their minds are clouded by the Book of Genesis. Belief in the first page of the Book of Genesis is deeply ingrained in the soul of most scientists." Fred Hoyle, despite being a highly accomplished scientist, is ironically best remembered for accidentally coining the term for a theory he opposed. As data accumulated that strongly supported the Big Bang, scientists inevitably began to ponder the logical question, what preceded it? However, all attempts to investigate this question have encountered a formidable obstacle known as the singularity, the point where the threads of causality converge. This problem has kept cosmologists on their toes, forcing them to search for scenarios to circumvent the original singularity. However, in 1970, physicists Roger Penrose and Stephen Hawking demonstrated with mathematical precision the futility of these efforts. Their proof claimed that the singularity must have existed at the moment of the origin of the universe. Does this mean that the ultimate origin of our world will forever remain a veil of mystery? Not necessarily. This suggests that the Big Bang cannot be exhaustively explained within the framework of classical cosmology, which relies solely on Einstein's general theory of relativity. Other theories must come into play. In contrast to Lawrence Krauss, the American physicist and cosmologist Alexander Vilenkin fervently insists that the universe came from nothing. Nothing is nothing. It is not just the absence of matter. It is the absence of space, the absence of time, the total absence of everything. However, as a physicist, he demonstrates a knack for ingeniously defining the state of complete emptiness. Such space-time is called closed because it is curved into itself. It is bounded, although it has no boundaries. Imagine a sphere shrinking like a deflating balloon. When the radius shrinks to zero, the surface of the sphere completely disappears, causing space-time itself to cease to exist. This scenario represents the epitome of nothingness, an enclosed space with zero radius. From a scientific point of view, this is the most precise and clear definition of the concept of nothingness, devoid not only of any content, but also of time or coordinates. Using this definition, Vilenkin performed intriguing calculations. Using the principles of quantum mechanics, he showed that from the initial state of nothing, a tiny patch of energy-filled vacuum can spontaneously appear. How small? Perhaps as small as 100 trillionth of a centimeter. Under the influence of negative inflation pressure, this fragment of energy vacuum undergoes unrestrained expansion. In a couple of microseconds, it reaches cosmic proportions, releasing a torrent of light and matter, the Big Bang. From the scientific point of view, this scheme looks flawless, and Vilenkin's calculations accurate. However, during a discussion with him, Jim Holt raised an objection. The bubble of false vacuum, which gave birth to the cosmos, had to come from somewhere. In response, Vilenkin suggested imagining a bubble of gas in champagne and then removing the champagne. The analogy suggests that the bubble in the champagne forms over time, but the very concept of nothingness has no time dimension. Accordingly, by definition, no processes can unfold in nothing. However, if Vilenkin's proposition holds true, then nothing never had a singular chance. In other words, the laws of physics, existing beyond the realms of space and time, dictate that the universe must exist with some non-zero probability. This raises the intriguing question of whether these laws are not merely descriptions of reality, but possess independent existence, even in the absence of space, time, and matter. On what tablets can they be written? To this, Vilenkin replies, "If you like, you can say that they are in the mind of God." In mathematics, nothingness is represented by the concept of zero. The invention of zero is attributed to Indian mathematicians. The Greeks and Romans couldn't have thought of it. How can nothing be something? The absence of zero in ancient mathematics prevented the development of a number system similar to the one we use today, where, for example, 906 means 9 hundreds, 0 tens, and 6 ones. In contrast, the Roman number system is not so simple. Indian mathematicians, influenced by Buddhist philosophy, easily manipulated the abstract symbol for nothing. As for the origin of the zero symbol, the historical evidence is inconclusive. According to one theory, it may have originated from the rounded imprint left by a coin in the sand, a material trace of the immaterial. Interestingly, Jim Holt notes that a large majority of mathematicians, about 2/3, hold a belief in something divine. This belief does not refer to the heavens inhabited by angels and saints, but rather to the realm of perfect and eternal objects that make up their studies, multiple spheres and infinite numbers, the square root of -1, and so on. Furthermore, many mathematicians believe they engage with this divine world through something akin to extrasensory perception, indicating a historical intertwining of mysticism and math. The mystical cult of Pythagoras, the originators of math as a deductive science, treated numbers as a divine gift, establishing a religious sect with a fervent devotion to numerical worship. Pythagoras declared, "Everything is number." Subsequently, Plato, under the influence of Pythagorean teachings, developed his own philosophical concepts. Interestingly, the term idea is attributed to Plato. He observed that mathematicians engage in reasoning about circles, perfectly round and infinitely straight lines that do not exist in the real world. For instance, consider a wooden wheel. While it may appear round, it merely aspires to achieve roundness. No matter the skill of a carpenter, they can never produce a perfectly round wheel with a precisely squared perimeter. Thus, any wheel on the planet is only a cast of some ideal round wheel that literally does not exist in our world. The same is true of numbers. The same is true of number 2, for example, must consist of a pair of perfectly identical units. But in the real world, no two things are exactly the same. Since such ideal entities cannot be found in the world that we perceive through our senses, since we can address them only mentally, then where are they? Plato concludes that the objects of such mathematical reasoning must exist in another world, eternal and ideal, the world of ideas, that the mind is given to us to perceive them, just as we are given eyes to see and ears to hear. And 2/3 of modern mathematicians agree with this. Among the most famous Platonists is Alain Connes, head of the Department of Analysis and Geometry at the Collège de France, who argues that there is an unchangeable mathematical reality independent of the human mind. Another contemporary Platonist, René Thom, who became famous in the 70s as the creator of the catastrophe theory, proclaimed mathematicians must have the courage to express their deepest convictions, and thus declare that mathematical forms really exist independently of the mind that studies them. Kurt Gödel was an ardent Platonist, arguing that we do in fact possess something of a perception of mathematical objects, despite their remoteness from sensory experience. I see no reason to trust less in this kind of perception, that is, mathematical intuition, than in sense perception. Gödel's belief in ghosts is a separate topic altogether. Plato's ideas attract many physicists who consider mathematical entities not only eternal and unchanging, but also influencing the formation of the physical universe. This is consistent with physicist Eugene Wigner's observation of the remarkable effectiveness of math in the natural sciences. So when you ask why postulate a whole separate mathematical world, when you can say that math is just a product of our imagination, you will be answered. Isn't it strange that some abstract things from our heads work so well in the real world? Physics is now simply impossible to imagine without math. Applying Galileo's idea that the book of nature is written in the language of mathematics suggests a fundamental mathematical nature underlying the world. Could mathematics contain the key to unlocking the mystery of being? Among contemporary Platonists, Roger Penrose stands out as a true genius. Here is a brief list of some of Roger Penrose's accomplishments and interests. Otherwise, if you don't know anything about him, you simply won't take seriously what follows. Roger Penrose, one of the most titled mathematical physicists, praised by colleagues such as Kip Thorne for reintegrating mathematics into theoretical physics. In the 1960s, along with Stephen Hawking, Penrose used advanced mathematical techniques to demonstrate that the universe must have arisen from a singularity. In the 1970s, he proposed the cosmic censorship hypothesis, arguing that each singularity is hidden behind the event horizon, preserving the integrity of the wider universe. Penrose played a key role in harmonizing the general theory of relativity with quantum mechanics and received a knighthood from Queen Elizabeth in 1994. For his contributions, in addition to his scientific merits, Penrose is known for his passion for the unusual. As an undergraduate, he studied the concept of impossible figures, physical objects, seemingly defying three-dimensional spatial logic. Penrose's triangle inspired Moritz Escher's famous lithographs. Remember this moment from the Christopher Nolan movie Inception.
That lets you create closed loops, like the Penrose steps.
Named in honor of him and his father, the continuous staircase was first introduced in an article Penrose wrote in 1959. Penrose won the Nobel Prize in Physics in 2020. Now, Roger Penrose is not at all shy about his commitment to Plato's teachings. In his writings and public lectures, he has made it clear many times that he considers mathematical entities to be real and as independent of the human mind as Mount Everest. He explicitly mentions Plato. In his book, The Emperor's New Mind, published in 1989, he writes, "I believe that when the mind perceives a mathematical idea, it comes into contact with Plato's world of mathematical concepts. Each mathematician entering this contact may represent something different in each case. But communication between mathematicians is possible because each is directly connected to the same eternally existing world of Plato." Occasionally, Roger Penrose suggests that even in our world, we encounter subtle influences from Plato's realm. In his widely successful 1994 book, Shadows of the Mind, A Search for the Missing Science of Consciousness, he contends that consciousness defies algorithms and cannot be adequately modeled even with formidable computing power. According to Penrose, consciousness has a quantum nature, and only with a yet-to-be-uncovered theory of quantum gravity can we hope to comprehend how the human brain gives rise to it. This perspective led to scrutiny from many neuroscientists. The late Francis Crick irritably remarked, "His argument is that quantum gravity is mysterious, and consciousness is mysterious, so it would be great if one explained the other." In fact, Penrose wants more than that. The very title of his book, Shadows of the Mind, has a double meaning. On the one hand, it is meant to imply that the electrical activity of brain cells, which is the source of our minds, is but a shadow of the underlying quantum processes taking place in the brain that are the true source of consciousness. On the other hand, shadows are a reference to Plato, specifically his allegory of the cave. So, Jim Holt met with Penrose to talk directly about this. Jim Holt: "Do you really believe in Plato's world existing above the physical world? Wouldn't the idea of two worlds be somewhat wasteful ontologically?" Roger Penrose: "There are actually three worlds, and they are all separate from each other. There is the Platonic world, there is the physical world, and then there is the mental world, the world of our conscious perception. The interrelationships between these three worlds are mysterious. Perhaps the main mystery I am working on is the relationship between the mental world and the physical world. How certain kinds of highly organized physical objects, our brains, produce consciousness. Another mystery, no less profound in terms of mathematical physics, is the relationship between the Platonic world and the physical world. In our search for the deepest understanding of the patterns of behavior of the world, we come to mathematics. Arguably, the physical world is built on math. It would seem that how can our physical brain interact with Plato's non-physical world? Each of the three worlds, the physical world, the world of consciousness, and the Platonic world, arises from a tiny particle of one of the other two, and it is always the most perfect particle. Take the human brain. If we look at the physical world as a whole, our brain is a very, very tiny part of it, but it is the most perfectly organized part. Compared to the complexity of the brain, the galaxy looks like nothing more than a clumsy lump. The brain is the most refined particle of physical reality, and it is this particle that gives rise to the mental world, the world of conscious thought. Similarly, only a small particle of our conscious thought connects us to the Platonic world, but it is the most impeccable particle, the one that consists of our reflections on mathematical truth. Finally, just a few bits of math in the Platonic world are necessary to describe the entire physical world, but these are the most powerful and astounding parts of it. Roger Penrose. And from Penrose's point of view, these most powerful and striking parts of mathematics are themselves capable of creating the physical world. And it is the Platonic world that is the source of reality. In Shadows of the Mind, he writes, "For me, the world of perfect forms is primary. As for Plato, The existence of this world is almost a logical necessity. Both other worlds are its shadows. To put it simply, the existence of the Platonic world is posited based solely on logic, while the realms of matter and mind are considered byproducts. Delving into the philosophical arguments of such a great mind is intriguing, yet at times it can sound like abstract discourse detached from reality. Paradoxically, as our scientific theories advance, they seem to become less grounded in tangible matter. The trend of dematerialization in scientific understanding traces back to Isaac Newton, who introduced the notion of action at a distance in his theory of gravity. Newton's law of gravitation describes the sun affecting the Earth through gravitational pull, despite the apparent absence of any material substance between them. The question arises, how does this interaction occur in the absence of intervening matter? Newton himself on this question modestly stated, "I do not invent hypotheses." If Newton dematerialized nature at cosmic distances, then modern physicists have done the same, but already at the smallest. In 1844, Michael Faraday noticed that matter cannot be recognized directly, but only by the forces acting on it. He then asked the logical question, why should we even think it exists? According to Faraday, physical reality does not actually consist of matter, but of fields. That is, they are purely mathematical structures defined by points and numbers. In the early 20th century, the notion of atoms, traditionally thought to be solid entities, was disproved as they were found to consist mainly of empty space. Quantum theory showed that subatomic components such as electrons, protons, and neutrons were not spherical objects, but rather clusters of abstract properties. At ever deeper levels, what was previously understood as material matter turned out to be fundamentally structural, although some might question this by claiming that objects do not pass through each other. The inability of two solid objects to penetrate each other is not due to the inherent hardness of matter, but rather to numerical constraints. Forcing two atoms to converge involves aligning their electrons in identical quantum states, which is a violation of Pauli's exclusion principle, which allows electrons to come together only if their spins are oppositely oriented. Preventing electrons from collapsing onto a nucleus within an atom is primarily a mathematical problem, because if the electrons were located on the nucleus at the center of the atom, we would know the exact location of each of them, as well as their velocity, which would be zero. However, this scenario contradicts Heisenberg's uncertainty principle, which prohibits the simultaneous determination of the coordinates and momentum of a particle. The hardness observed in everyday objects such as walls, floors, and stones is the result of the Pauli exclusion principle and the Heisenberg uncertainty principle. In essence, what is commonly referred to as hardness can be explained by a couple of abstract mathematical relationships. At a fundamental level, science describes the elements of reality in terms of their interrelationships, disregarding any inherent material characteristics of those elements. For example, although science attributes certain properties of mass and charge to the electron, these are merely attributes that affect how other particles and forces interact with the electron. Science recognizes the equivalence of mass and energy, but does not go into the nature of energy, which is not a numerical quantity that is conserved in physical processes. As Bertrand Russell noted in the analysis of matter, when it comes to the true nature of entities, science remains silent, providing only a tangled web of interconnections, a structure without matter. The latest development in the ongoing dematerialization of nature is string theory, which constructs matter from pure geometry. String theory is one of the main contenders for an elusive theory of everything, potentially more profound than the quantum cosmologies of Hawking and Vilenkin. String theory, for example, allows us to speculate about a reality that existed before the Big Bang, when the concepts of space and time had no meaning. Steven Weinberg, a prominent physicist, played a central role in the search for the final formulation of the theory. In 1979, he won the Nobel Prize in Physics for his contribution to unifying two of the four fundamental interactions, the electromagnetic and weak interactions. In his book, Dreams of a Final Theory, he writes, "The discovery of a final theory may bring disappointment because nature will become more ordinary. There will be fewer wonders and mysteries." As we can see, he did not believe that a theory of everything could explain really everything. But what part of the cosmic mystery is Weinberg talking about? According to him, the answer to the question of why there are some laws in the beginning depends on what the final theory turns out to be. Let's say it turns out to be like Newton's theory. Newton's theory has a clear separation between laws and initial conditions. For example, Newtonian physics says nothing about initial conditions in the solar system. Newton himself understood this and believed that the initial conditions were laid down by God. If the final theory leaves the initial conditions unexplained, then, even if it fully explains the process of the development of the universe, the origins of the universe will remain shrouded in obscurity. Who or what established these initial conditions? Steven Weinberg. Einstein once said, "What I'm really interested in is whether God had any choice in creating the world." In other words, is it just pure chance that our universe has such friendly qualities? Or if we knew all the laws of physics, we would realize that the universe simply cannot be any different. Why are the fundamental constants so tweaked that the world has the potential for complex life to evolve? Change just a little bit of anything, and it all collapses like a house of cards. Weinberg, this obvious subtle customization, simply amazed him. He believed that the only explanation for it other than the divine could be given only in terms of a multiverse. That is, a universe made up of many parts, each with different laws of nature and different values of constants. Most are not suitable for life, but some are conducive to it. I do not claim that a multiverse will resolve all philosophical questions. It will only relieve us of the wonder that the conditions in our universe are so well suited to the development of life and intelligence. Steven Weinberg. You see, Weinberg goes beyond the standard notions of the multiverse. When we hear about fine-tuning, we are really surprised. We find fascination in conceptualizing fine-tuning as adjustable sliders, each representing a distinct fundamental law, finely tuned to permit the existence of life. We often contemplate the possibility of multiple universes, where these sliders are set differently. However, a more remarkable aspect tends to be overlooked. The question arises, why do these fundamental laws possess their specific characteristics? Why are they not different? And why do we have precisely the number of laws we observe? Consider the scenario where only half of these laws exist in our world, or more challenging to envision, if there were twice as many laws. To illustrate, consider computer games, a shooter and a strategy game. These games feature fundamentally different parameters. In a shooter, one can adjust the character's jump height, while in a strategy game, not only is such a parameter absent, but there are no jumps at all. Conversely, in a strategy game, you may manage economic indicators, a mechanic absent in a shooter. Additionally, the world in a shooter is three-dimensional, whereas in a strategy game, it is two-dimensional. In short, the universe of both games has completely different laws. These two games are absolutely different from each other, but nevertheless, most importantly, they both run on the same computer. What's my point? Steven Weinberg, to repeat, goes beyond the idea of a multiverse with simply different meanings of the same laws. And in his book, Dreams of a Final Theory, he mentions the idea of Harvard philosopher Robert Nozick. He writes, "But why should a final theory describe something like our world? The explanation may have to do with what Nozick called the principle of fecundity. He argues that all logically possible universes exist in some sense, each with its own set of fundamental laws. The fecundity principle itself is not self-explanatory, but there is at least some nice self-consistency to it. As Nozick writes, the principle of fecundity asserts that all possibilities are realized, including the possibility that the principle itself exists." Steven Weinberg, in conversation with Jim Holt, ponders a scenario that may be difficult to fully grasp. If the principle of fecundity is true, then reality extends infinitely beyond our imagination. Within this framework, our universe looks remarkably modest, because all logically conceivable worlds exist alongside it. These worlds include all sorts of possibilities, ranging from a universe with a single electron and positron spinning around each other, to worlds very similar to our own, worlds inhabited by Greek gods, and worlds made of cheese, and worlds where everything is exclusively red. Countless other worlds have properties that we cannot imagine. Crucially, these worlds lack causal relationships, and the transition from one to another is likely implausible. It is noteworthy that this concept is supported by noted scientist and skeptic Steven Weinberg. Jim Holt, after dialoguing with Weinberg in his book, expresses surprise at Weinberg's openness to such metaphysically extravagant ideas. It is important to note that Weinberg does not claim that this scenario necessarily occurs. He simply highlights its possibility and finds it to be a thought-provoking concept. The completeness principle, if valid, offers an explanation for nearly everything. It addresses the questions of why the world has its current state and why we exist. The answer lies in the assertion that everything, not mathematically inconsistent, exists, encompassing worlds with fundamental laws like ours, where some configurations allow for the potential origin of life. However, the lingering question of why there is something rather than nothing remains. If we posit that both exist according to a given principle, the principle becomes internally contradictory in this formulation. Steven Weinberg suggests that a theory of everything can potentially provide insight into why anything exists. For instance, the laws of nature might necessitate the existence of something, fundamentally prohibiting a state of true nothing. Here again, in his assumptions, he is in harmony with Robert Nozick, who in his latest book, Philosophical Explanations, writes that perhaps nothingness as an annihilating force annihilates itself, thus giving rise to being, and thus there can be no nothing, and being simply has no alternative. This presents an intriguing paradox. However, what about us? The palpable nothing we experience after death seems quite real, doesn't it? Arthur Schopenhauer became famous for the major work of his life, The World as Will and Representation. Conrad Watchman, a friend of Einstein, recalled, Albert often sat with one of Schopenhauer's tattered volumes and seemed so contented, as if he were engaged in a serene and cheerful endeavor. Einstein considered Schopenhauer a genius. Rudolf Kaiser, Einstein's son-in-law and biographer, said that in the late 1920s in Einstein's office in Berlin hung portraits of three men, James Clerk Maxwell, Michael Faraday, and Arthur Schopenhauer. Charles Darwin referred to Schopenhauer's The World as Will and Representation in his work, The Origin of Man and Selection According to Sex. Nobel Prize-winning physicist Erwin Schrödinger's philosophical views were shaped directly by Schopenhauer's ideas. Schopenhauer, influenced by Plato's notion of an eternal world of ideas, giving rise to our sensual world, incorporated this concept into his philosophical system. According to Schopenhauer, in his philosophical system, our existence is indestructible. He rejected the existence of God and the soul, as well as the possibility of preserving personality and memories after the destruction of the body. In his work, he argues that the core of reality is a blind, insatiable, unconscious force, which Schopenhauer calls the will, and the whole world given to us in sensations is its embodiment. The will is the very core, the nucleus of everything private, but also of the whole. It manifests itself in every blindly acting force of nature, but it is also manifested in the deliberate activity of man. The great difference between them concerns only the degree of manifestation, but not the essence of what is manifested. Arthur Schopenhauer. How absurd, you might think. How can the will express itself in a mere rock, peacefully traversing space? Yet, it can. A rock exhibits a tendency to resist both internal and external influences, requiring effort to alter its shape, direction, and speed. Going further, considering that greater mass locally decelerates time, a rock warps space, attracting other matter to extend its journey into the future of the universe. In this perspective, what we term gravity becomes the tangible manifestation of objects' desire to endure in space as long as possible. It is the force that moves and vivifies plants, that forms the crystal, that directs the magnet toward the north. It is the force that meets it with a blow when dissimilar metals come in contact. It is the force which, in the affinity of material substances, manifests itself as repulsion and attraction, separation and union, and finally as gravitation, so powerful in all matter, drawing stone to earth and earth to the sun. Arthur Schopenhauer. And man, cognizing reality, is nothing else but the representation of the world's will of itself, to itself, as if its act of self-knowledge. The will cannot be destroyed, for it is the fundamental force generating the universe as a whole, and man in particular. Therefore, after the death of the body, it finds itself in a new intellectual shell. Thus, according to Schopenhauer, nothingness does not exist. As for the individual consciousness connected with the body, it is completely interrupted every day by sleep. Deep sleep, while it lasts, is no different from death. It differs from it only in its relation to the future, that is, awakening. Death is a dream in which individuality is forgotten, yet the other wakes up again, or rather, it has not fallen asleep at all. Therefore, whoever is satisfied with life as it is, who affirms it in every possible way, can hopefully consider it endless and banish the fear of death as an illusion, inspiring a ridiculous fear of ever losing the present and deceiving him with the ghost of time. Arthur Schopenhauer. It is indeed a beautiful and intriguing concept, providing an interesting way to reject one's mortality. However, Schopenhauer held a different view, expressing his unwillingness to be condemned to eternal existence and preferring a post-mortem state of blissful nothing. Your views on this subject would be greatly appreciated. Feel free to share your thoughts in the comments. Thank you all for watching.